Now let's look at example 7.1. Okay, it's a relatively simple example. Okay, but calculations, right? It's something that you need to pay attention to, and that's really nothing new. Okay, the math, the equation is something that you're really familiar with. Okay, you just use the same procedure for any other situation. Right? Anything more complicated than that, no problem. Okay, let's look at the structure right here. Now you have this rigid body AD. Okay, this little piece of metal. Okay, a beam. Okay. At D, you're attached to the ground. Okay, and it's a connection, so it's free to rotate. Okay. At A, it's just a little support, and that's all. It's not attached to it at all. Okay, so it's just resting on the ground. Now, there are two external stuff going on. First, you have this 6,000 Newton force coming straight down at this position. And also you have this couple moment being applied, external moment applied counterclockwise, right? 9,000 Newton meters, okay, of moment. You're asked to find the internal forces and moment at B and C, where B is just left of this section right here, where this 6,000 Newton is applied, and C is just to the right of it. Some dimensions are given. Okay. Let's start analysis. First thing you do, the very first thing, before you just do any cutting, first look at the entire thing. Look at the free body diagram for the whole rigid body. Okay? So, let's do it here. Free body diagram, whole thing. So, the whole thing is AD. And then you draw all the forces and moment. Okay? So here we have 6,000 Newton. And we have 9,000 Newton meter of moment. So these two are the applied, externally applied force and moment. What else? Well, we have this connection right here. Right? Since it's free to rotate, okay, now we have a reaction force. Okay. Let's call this reaction force FD. And also, now since this kind of connection, okay, it resists any potential movement, okay, of this point D vertically as well as horizontally. Really, you should have a horizontal reaction force as well. So let's call this FDY, FDX. Okay, what else? Well, this point, A. Now, this A is just simply resting on the ground. Okay? So, there's only one reaction force, which is perpendicular, okay, to the ground direction, which is this way. Okay? So this is my reaction force at A. That's it, just one component, vertical component. Alright, so this is my free body diagram for the whole rigid body. Now, in this analysis, and in most of our analysis, we make the assumption that the mass of the rigid body itself is ignored. Okay? Typically, they can't be ignored if all these external forces are much bigger than the weight of the rigid body itself, okay, which is our assumption here. Okay, so we're not going to consider weight right now. Okay, and we'll start considering the weight after we talked about something called the center of gravity. Okay, and that's later chapters. Okay, so for now, let's just keep it simple. Okay, assume that mass is ignored. So the free body diagram looks something like this. Now, the goal here is to find the internal forces, right, at B and at C. Let's look at B first, right? So what's going on here at B? Well, that means that you need to cut through this B point, right? And I like to keep things simple, so I'm going to take this AB section. If I take this AB section, that means that I need to know what's going on here at A, which means that I need to find FA. Okay? So I find FA from this free body diagram right here. Okay. How do I find FA? Well, what equation do I have? Well, this AD has to be in equilibrium. So I have some forces X equal to 0, some forces Y equal to 0, and some moment equal to 0. Which equation will allow me to find FA? This is useless because FA is in the Y direction, right? Where X and Y is applied this way, right? Conventionally. Fy, the second equation, is useful. Well, okay, Fa will appear in this second equation right here, right? Okay, I know this, no problem. Okay, this will appear also, but I don't know Fdy. Okay, so there are two unknowns here from this equation. That's useless as well. How about this equation? From a moment equation. Now, this could be useful. Next question is some moment about what point. Now I have a lot of unknowns going on here, so I need to pick a point where some of the unknowns are eliminated. They don't appear in this equation. Okay? A trick that you already know, right? We've done so many times now. So, the point where we want to take moment about is point D, where these two unknowns pass through D. Okay? So, I'm going to use this now. So, some moment of point D equals 0, so I have FA, where clockwise direction is positive. So FA times, well, the moment arm, which is this distance right here, which is 9 meters, minus 6,000 Newton, coming down, well, counterclockwise direction, that's why it's negative, times the distance is 6 meters, moment arm. And don't forget this applied moment, this couple moment, right? So it's in the counterclockwise direction. That's why it's negative 9,000. And that's it. Equal to 0. Now you can crunch numbers, right? So move that over to 6,000 times 6 plus 9,000 divided by 9. Okay, so 36,000 plus 9,000 divided by 9. Right, so you have 45,000 divided by 9. Okay. So you get 5,000 units. Okay. So FA is 5,000 newtons. It's a positive number, which means that this direction is correct. Okay. So I've done the correct, assumed direction, correct direction. Okay, for this reaction force FA of 5,000 newtons. Okay, now that I've found FA, I can proceed to the next step. Okay? Okay, and try to find what's going on here at B. So, what you want to do is just cut through B. Now B is just left of this point, this section right here where this 6,000 newtons applied. Immediately left of it. Okay? So now I have drawn B to be quite far from it, but really, we're really interested in looking at what's going on just to the left of it. Alright? So this distance, 3 meters, will still apply. Okay? Although it's slightly less than that, but okay, we can still apply 3 meters. Okay? So, section AB. So free body diagram of AB. So let's draw that. A, B. And then you draw all the forces. Alright? So here, A, what's going on A? Well, you do know that FA of 5,000 newtons. Okay? Is being applied upward. What else? Well, we have B. Okay? Now, from previous discussion, you do know that there's 3 things going on at B. Okay? You have these 2 forces, the normal force, the axial force, the shear force, right, at the moment. Okay? So, just to be consistent with the nomenclature of the textbook, I'm going to call this N, and normal force at B, this is shear force at B, and this is bending moment at B. Okay. So you have these 3 unknowns, okay, for this one free body diagram. So next thing you do is just multiply the 3 equations. Equals 0. Sum of forces y equals 0. Sum of moment equals 0. 3 equations, 3 unknowns, no problem, right? So, first equation, sum of forces x direction equals 0. So, looking at this whole free body diagram, I have normal force or axial force at B. That's it. So NB equals 0. And that's quick, right? NB, by the way, we decided that it doesn't exist. Okay? That means that anywhere inside this member, okay, at least here in this section, there's no axial or normal resistance. Okay? So everything is up and down. Okay? Which is the prayer. Right? So apply this equation to this free body diagram. Now we have 5,000 newtons going up, so positive. And we have, now this I have drawn the arrow to be going up. Now that's my assumption, okay? So that's why it's positive. The B force, this shear force, and that's it. There's no other Y forces. This equals 0. Therefore, VB equals, we got over, negative 5,000 newtons. It's negative. Negative means my assumption is incorrect. Right? So